Hello everyone, AB Calculus section 1.2, day number 2, representations of functions. Our objectives for this lesson are the slope function and area function, transformations performed on functions, and how to find the intersection points of two functions. A slope function is the slope function g of x is the slope of the curve y equals f of x at any point x f of x. So in example 1, let's find and graph the slope function for f of x shown below. Okay, so let's write an equation first for the slope function. So as we look at this piecewise function, it has 3 portions to it, all of which have different slopes. So on the first portion of the slope function, let's define the slope function as m of x. I'm not going to use g of x, let's use m of x. Okay, we have a slope of positive 1 based on the graph. Now, one thing that you're going to want to notice here is that at each of the points where these piecewise portions of the graph meet, there is no slope, right? It's going from a slope of 1 to a slope of 0. No slope exists at any joint unless those two slopes are smooth and continuous there. So as we look at this, we would say that m of x is equal to 1 when x is less than 0. Then we transition to the second portion of the graph, which is a slope of 0 from x equals 0 up to x equals 3. And then from there, we transition to a negative slope. It looks like negative 2/3 when x is greater than 3. Let's sketch this graph. So m of x's graph would be 1 up to 0, x equals 0. Then it transitions to a slope of 0 up until x equals 3. And then it transitions to negative 2/3 for the remainder of its graph. So that step-looking function would be m of x. All right, let's look at another example. It says graph f of x given below, then find the slope function for f of x. All right, so it looks like we have 4 pieces to this piecewise function. And it looks like the joints of each of the piecewise portions are at x equals -1, x equals 0, and x equals +1. So f of x equals negative, let's see some colors here. Negative x minus 1 if x is less than or equal to -1. So we would have a slope of -1 here on that portion of the graph. For the second portion of this piecewise function, we would have x plus 1 when x is between -1 and 0, inclusive at 0. You can see how I'm noting the open interval or closed interval portion of that boundary. Okay, the third portion, f of x equals negative x plus 1 from 0 up to 1, inclusive at 1. And then the last portion would be open at x equals 1 and a slope of 1 there. So let's write an equation for m of x. So the slope of the yellow portion of the piecewise would be -1 when x, again, remember you're never going to include an endpoint if it's not a smooth slope at that joint. X is less than -1. Green portion is 1 when x is between -1 and 0. -1 when x is between 0 and 1. And then +1, looks like it's alternating between the two when x is greater than 1. There you have it. That is the slope function. Now you might ask yourself, how would you write a slope function for a non-linear function? That's a great question, and that will be something we answer in chapter 2. All right, so let's move on to the next topic. The next type of function that we're going to write is called an area function. So the first thing we have to do is we have to be able to write an equation in piecewise form for the actual function itself. It'll be helpful in the process. So let's write a piecewise function for this graph over here, f of x. So it looks like there's two portions to f of x, and they transition at the point x equals 3. So when x is between, I guess we could include 0 and 3, the function takes on the form of 2x. Slope of 2 on the interval from 0 to 3. From there, it looks like the output for f of x is always 6 when x is greater than 3. One thing to note, we've talked about this before, we can't have a portion of the function and the other portion of the function share one of these boundary points. So I could have left it open here at 3 on 2x and closed it on 6, or the other way around as I did. Okay, so let's find the area, a of 3. What that means is the area accumulated from the starting point x equals 0 up to 3. So you'll see that we've got this triangular space here. All right, so a of 3 is just the area of a triangle. 1/2 the base, which is 3, which was our x value, times the height, which was 6, which is our y value. Okay, that's interesting. And the 1/2 won't change on that interval due to the fact that it's a triangle. Okay, let's find a of 6. A of 6. Well, a of 6 would be a of 3, so the area accumulated, plus then the area accumulated afterward. So let's find a of 3. Looks like a of 3 would be 18 divided by 2, which is 9. Plus, now we're going to accumulate a rectangle. Now that rectangle in this case will be base, and if we go out here to 6, the base of the rectangle would be represented here by 3. So I'm going to take the base of the rectangle, which would be 3, times the height, which would be 6. So we're going to get, what is that, 18 plus 9, so a of 6 is equal to 27. Now how did I find the area of that rectangle? Well, this was f of x right here, which is always 6. And this over here was the distance between x and 3. So we took 6 minus 3 and got 3. That's going to be useful here as we write the area function for that graph. So the area when x is less than or equal to 3 will be equal to 1/2, as we said, the x value times f of x at that value. So that'll be 1/2 times x times f of x, which on that portion of the piecewise function is 2x. Okay, I could rewrite, and I'll do that in a moment here, cleaning this up a little bit. It looks like that'll be the 1/2 and the 2 will reduce, giving us x squared. Okay, let's look at the remainder of the area function, which is when x is greater than 3. So first thing we'd always do if x is greater than 3 is we'd add the area accumulated up to 3, which is 9. Plus, now we're going with a rectangle for the remainder of the area. So like we had, if x equals 6, I've got a rectangle with a base of 3 and a height of 6. Since the height, or that output, the height of the rectangle won't change, I will just take whatever x minus 3 is, and I'll multiply it by 6. Okay, now we can manipulate this and make it simpler. I believe that this would be an acceptable answer for the area function, but I want to clean it up just a little bit. If I clean it up, I would get 6x It looks like -9 when x is greater than 3. So if I wanted to know the area when x equals 10, I would take and simply work with the fact that that falls with an x value that's greater than 3. So we would have 6 times 10 minus 9, which looks to come out to be 51 units squared. Okay, let's look at another example using an area function. Okay, it looks like I'm going to need to graph this one. So I'm going to graph the two portions of the piecewise function f of x, where the first portion is t plus 1. Looks like we're just using t as a variable here. So t plus 1 would start at 1, and over an interval of 3 units would go up to t equals 4. So it looks like on this portion of the piecewise function, I would have a trapezoid. So we're going to be working with trapezoidal area here on this next area function. Okay, now the second portion of the piecewise function is t minus 9. So the second portion will be a trapezoid up until the point t equals 7. Okay, so we've graphed f of x. Here's f of x. Let's find some areas. So a of 2. Let's remind ourselves here, what's the area formula for a trapezoid? Well, that is 1/2 base 1 plus base 2 times the height. Okay, so let's look at a of 2. A of 2, let's put a 2 here. Looks like I've got a trapezoid, and its two bases are 1 and 3. And its height is the distance in between, which will be 2. Let's isolate what this means. The 1 will always be a 1. That's not going to change. The 3 is going to be the output of the function. So how did I get a 3? I took t plus 1. And the 2 is the t value. So that's going to tell you a little bit about our formula if we were to work between 0 and 3. So a of 2 is going to be 1/2 of 4 times 2, which would be 4. All right, now a of 6 is going to require us first to find a of 3. I would work my way to the end of the first interval, and then I'm going to work a trapezoid on the other side. So first let's find a of 3. A of 3 will equal 1/2, 1, which doesn't change. F of 3 ends up being 4, and the height is the distance between, which would be a length of 3. So it looks like I would get 15 halves. I think that'll be beneficial to leave it in that form. Now the area from 3 up to 6 just so happens, you guys, in this case, just so happens to be symmetrically equal. Right? You can see that these two will be the same. Okay, so I could really just double the area from 0 to 3, and that would give me that entire area for a of 6. So a of 6 should end up equaling 15. But I do want to build this thing, so let's do it. So in order to find this area, this green space, I'm going to take 1/2 base 1 plus base 2. Well, base 1 will always be 4. 4 plus whatever my x value is. So let's say here it's 6, right? So that would be a length of 3. If it was 5, that would be a length of 2, etc. So in this case, I will utilize 3. Excuse me, not 3. I will utilize a height of 1, and then the distance between is 3. So where did I get the 4? Well, the 4 is not going to change. It'll still be a 4. The 1 will be the output, right? So the output of negative t plus 7. And then the 3 will be t minus 3, right? That's the length right here. So 1/2 of 5 times 3, 15 halves. So I had 15 halves plus 15 halves. Now, By symmetry, I could have seen that earlier, but I wanted to build that. So let's build the area function in terms of x. And we've kind of already done it. We took a 1/2, and of course, oops, I had a little mistake up here. I took 1/2. The first base here will always be a 1. The second base will be whatever f of t equals at that x value. So base 1 and base 2 will always be 1 and t plus 1. And the height, the height of the trapezoid will always be the t value. So let's isolate this. This is 1. The other base will be t plus 1, and the height between the two bases will always be t on that first interval. Okay, and that is always good for t between 0 and 3. On the second portion, of course, we would take a of 3, which is the area accumulated from 0 to 3, plus trapezoid 1/2 base 1 plus base 2. Base 1 will always be 4. That's f of 3. And base 2 will always be negative t plus 7. Whatever the t value is, that will help us to determine the second height. And of course, the length between the two t values will be whatever t is minus 3. Now, I don't think I'm going to go ahead and clean that up too much. I'm just going to leave that. And I believe I can go ahead and safely say that that's when t is greater than 3. Okay, so again, area of a trapezoid is 1/2 base 1 plus base 2 times the height or the length between the bases. All right, we got one more slide here. Let's get to it. Okay, guys, some transformations on functions. Two parent functions that we're working with here. I'm going to call them both h of x, or the square root of x, and h of x, the parent function over here, is the absolute value of x. And with both of these functions, they have very special points that are important, that help to kind of distinguish and set the pattern of how the function develops from there. With the square root of x, it is that spot right here. I don't know what you'd call that point, but 0, 0, right? It's where the square root starts. Okay, it's the end of the domain on the left side, and it goes to this point 1, 1. So I'm going to perform just a transformation upon that. Now, any transformation that takes place inside the function is a horizontal transformation, and it's always the opposite of what you think. So horizontal transformation would be left or right. In this case, this function would be transforming by doing a shift, and it's going to go left, right? The opposite of what you think, 3 units. So it's going to take these 2 points and it's going to shift them over 3 units. So this would be the point -3, 0, and this would be the point -2, 1. Now, there's also a vertical transformation going on, and this vertical transformation is a vertical reflection. That'll be over the x-axis. So it's going to take, and it's going to reflect this point right here beneath the x-axis. So this would be a graph, of course, still containing the point -3, 0. Since there's been no vertical shift, that point won't change in its, at least in its y value, but it will reflect -2, +1 to -2, -1. So this is kind of like a guiding point right here, which can kind of tell you where the function is going to end up. Same is true over here for h of x, right? So the absolute value of x, it's got what I would call its vertex right here at 0, 0. Now I'm going to shift that vertex around. So the first thing I'm going to do is I'm going to take g of x and reorient it just slightly. And I'm going to factor out a 2 inside the absolute value. So what's going to be happening to the vertex is it's actually going to shift right 3 units, and it's going to shift up 5 units. So I'm going to go to the right 3 and up 5. That's where our vertex is going to land. Now the rest of the transformations, you know, you might have a vertical reflection, so it could open downward or upward or be stretched or shrunk. We have to look at that now within the context of this problem. So here I've got another horizontal transformation going on. And of course, this is a horizontal, don't get fooled, shrink by a factor of 1/2. It's always the opposite of what you think. So I see a 2, I think stretch, but it's not. It's horizontal shrink. So if you analyze the absolute value function, this is a slope of 1. This is a slope of -1. So within the context of this, shrink by a factor of 1/2 would turn the slope now into a slope of 2 and -2. So it's like a vertical stretch. So if I were to put 2 more points on this, this would be the 0.4, 7. And likewise on the other side would be 2, 7. So it's been stretched vertically, which is the same as a horizontal shrink. Okay, let's look at intersecting functions to finish the lesson for this video. Example number 6 says find the point or points where f and g intersect. So analytically, what that means is I'm just going to set f of x equal to g of x. Okay, so I'm going to FOIL x squared minus, or x minus 4 squared, which is x squared minus 8x plus 16, and I'm going to add the 2 to that, so that'll make plus 18. Probably going to have to use some factoring methods here, hopefully not quadratic formula, but it looks like I get x squared minus 10x, combining like terms, plus 21. Ooh, that's going to be factorable. I like that. So it'll be x minus a 7 and x minus a 3. So using the zero product property, if x minus 7 times x minus 3 equals 0, then either x minus 7 equals 0 or x minus 3 equals 0. Thus, at the point x equals 7 and at the point x equals 3, the two functions intersect. Now, what would that look like? I don't have my graphing calculator available here, but I'll just sketch a general graph. So this will give us an opportunity to graph some functions. This is a quadratic that opens upward, right, because a positive leading coefficient. It's been shifted 4 right and up 2. So 4 and 2. General sketch, f of x would look like that. Okay, and g of x is going to equal 2x minus 3. So g of x would be y-intercept of -3 and a slope of, it looks like 2. All right, so there's a graph of g of x. Now, where do they intersect? They intersect at those following 2 points. This one would be at x equals 3, and not well sketched, but that would be at x equals 7. Now, if it's asking us for the actual coordinates, I could find the actual coordinates. So if x equals 3, I could plug it into either of the two, since it's where they intersect. So g of 3 is equal to 2 times 3 minus 3, which would be 3. So f of x is equal to g of x at the point 3 comma 3, and, that was a weird and, at x equals 7, g of 7 is 2 times 7 minus 3, which would be 11. So that would be at the point 7 comma 11. And there you go. You got the two solutions to where f of x is equal to g of x. We will see you in the next video, folks. Have a great day.